Hello and welcome to the course of Computer Network Part 2. And today we are going to discuss one of the intra-domain routing protocol which is used for providing routing inside an autonomous system. And that protocol name is distance vector. And in the last lecture, we discussed link state routing algorithm, um, which is again a intra-domain routing algorithm. So it's a bit different and uh, from the link state routing algorithm, because link state routing algorithm is it's a global routing algorithm, and distance vector routing algorithm is a decentralized routing algorithm, and distance vector routing algorithm is completely based on the Bellman-Ford equation. So let's see how it works. So let's assume a network in which you have two nodes X and Y, which are very far away from each other. So if we have to apply a distance vector algorithm to find out the shortest distance between these nodes, then Bellman-Ford has given this particular equation which you see in front of you, dxy. It is the cost of the least cost path from X to Y. And how you're going to calculate it? It's minimum of these things which you have in the curly braces, cxv. It's a distance from X to its neighbors. So we are here, we are the neighbors over here. V can be any number. It can be like 2, it can be 3, it can be n, plus dvy, again the same thing, distance from a neighbor to the final destination, which is y. So we have to find out distance from X to Y through all the neighbors of X, which are V in this case. So out of those distances, whichever is a minimum will be the final cost from X to Y. Let's understand this particular Bellman-Ford equation with example which you see in front of you, that we have a autonomous system which has got 6 router, and if you want to calculate minimum cost from node U to Z, so you can see that U has got 3 neighbors. Neighbors are those which are directly connected with that particular node. So U is got V, which is directly connected with distance of 2 with a cost of 2. X is directly connected with U with a cost of 1, and W is directly connected with U with a cost of 5. So Bellman-Ford says if you want to reach from U to Z, then you have to find out the cost from all your neighbors to Z, and then whichever is minimum would be the final cost. So you can see over here that U's got 3 neighbors. So finally, what all you have to calculate is uh, the minimum cost of the path, which is U to Z. So here you have got 3 neighbors, which you can see dv, dx and dw. So these are pre-calculated, because again you have to apply the Bellman-Ford equation in the same way as we are going to apply the Bellman-Ford equation to calculate the distance, shortest distance from U to Z. So it's already done. From V to Z the shortest path is 5. X to Z, the shortest path is 3, and from W to Z shortest path is 3 via this way. So now according to Bellman-Ford equation, duz would be minimum of uh, these 3 values going to zy via u going to z via x going to z via w. So you can see over here that c uv would be is it's directly connected with v, so it would be uh, 2 2 plus 5. You can see over here 2 is the cost from u to v, and then v to z is 5, so here 2 plus 5. Then again you will calculate with the second neighbor, that is x, so it's 1, and then x to z is 3, so it would be 1 plus 3, and then the third neighbor is w, so it's directly connected cost with w is 5, and 5 plus 3 via this way, it would be around 8. So out of these three neighbors, x will get you to z in a shortest way, because you can see it costs only 4. So that is how Bellman-Ford equation works for you. And you can see in this equation that for all the equations with the neighbors, you have to calculate this again as we did this. So if you want to calculate dvz, then dvz would be like you have to go from v to z through all the neighbors of v. So here we have got one directly connected neighbor, two directly connected, the second directly connected neighbor, and this one is the third directly connected neighbor. So that is how it's gonna work. You have to calculate vz through all its neighbors, and whichever is got the minimum cost, you have to finalize that. So that is how Bellman-Ford works, and we'll see the example of Bellman-Ford shortly. So here dxy, as we all know that it's a distance from x to y, estimate of least cost from x to y. X maintains distance vector dx, which is dxy, y belongs to n. For node x, knows cost to each neighbor, that is what distance vector is, which is c, cost from x to v, which means node present in an autonomous system at least knows about its neighbors and its cost to their neighbors, maintains its neighbors distance vector. For each neighbor v, x maintains this dv is equals to dy, where y belongs to n. And the key idea behind this distance vector algorithm is from time to time each node sends its own distance vector estimate to neighbors. When x receives new dv estimate from neighbor, it updates its own dv using Bellman-Ford equation, which we have discussed in the last couple of slides. And once you are done with that and you find any change in the cost to the destination at your node, then you need to share that information with your neighbors as well. So under minor natural conditions, the estimate dxy coverage to the actual least cost dxy. So its distance vector routing algorithm is iterative, and it's distributed, iterative, asynchronous. Each local iteration caused by local link cost change, dv update message from neighbors, distributed. Each node notifies neighbors only when its dv changes, as I told you in the last slide. Neighbors then notify their neighbors if necessary. So here is the main thing, that each node waits for change in local link cost or message from neighbors, then it recomputes, estimates cost to the distance. If it finds any changes, if dv to any destination has changed, notify neighbors. So this is all about distance vector routing algorithm. So let's discuss this routing algorithm with a example. It's a small network which you see at the right side of your slide, which has got X, Y, and Z nodes with with their respective costs, which you can see X is connected with 2, Y is connected with Z with 1, and X is connected with Z, directly connected with Z with the cost 7. So how you will proceed with the algorithm is, first of all the nodes have their personal information, and that personal information is nothing but cost to their directly connected neighbors. So this particular table is for node X, and directly connected neighbor for X is Y and Z, and X knows how to reach directly to Y with the cost 2, and X knows how to reach Z because it's directly connected with Z with the cost 7. So here you can see in this particular table that X, it's a simple table where X to X is 0, X to Y is 2, X to Z is 7, and you can see Y to X is infinity, Y to Y is infinity, Y to Z is infinity. It means this particular table is only for X, and in the same way the table for is Y knows only about these two directly connected neighbors X and Z. You can see over here that Y to X is 2, Y to X is 2, Y to Y is 0, and Y to Z is you can see Y to Z is 1. So it's a simple table for node Y, and in the same way you have simple table for node Z, because node Z is got two nodes which are directly connected with it, X and Y, and you can see Z to X is 7, Z to Y is 1, and Z to Z is 0. That is quite obvious. So according to the algorithm, all the nodes present in this autonomous system will share their personal information or personal routing table with their neighbors. So here you can see the arrows that this autonomous system is got three uh, nodes. So X will share its personal information with Y and Z. You can see these two arrows. Then Y is going to share this personal information of its with X and Z, and Z will share its personal information with Y and X. So the first is you can see X node is got the information of Y and Z. That means Y and Z both are sharing its information with X, and X is got its information here. So what is going to happen is, after receiving these information from its neighbors, X has to recompute its cost to their directly connected neighbors. So that is done with the help of Bellman-Ford equation. So you can see over here that X to X would always be 0, shortest. Now you can see X to Y, X to Y, and via all the neighbors. So here is got, we have got Z. So you can see over here that X to Y plus Y to Y, and the second is only neighbor is Z other than Y, so it would be X to Z, then Z to Y. So this is the Bellman-Ford equation for X to Y in this particular small autonomous system which has got only 3 routers. So you can calculate this distance. X to Y is 2 plus Y to Y is 0, and X to Z is 7 plus z to y is 1, so it would be around 2 and it would be around 8. So minimum would be 2. So it will remain as it is. It will remain as it is. You can see over here, it will remain as it is. Now it will calculate the distance for z. X will calculate the distance for z with the help of two tables shared by y and z. So now you can see that for calculating or recomputing the distance from x to z with the help of these two tables shared by y and z, again x has to apply Bellman-Ford equation from x to z, and now x to z. So x is got another neighbor y. So here first of all it's x to y plus x to y plus y to z, and the second one is x to z and z to z. You can see over here the old one. So after calculating it, x to y 2 and then y to z 1, so it would be around 2 plus 1 3, and the old one is x to z is 7 and z to z is 0, so it's 7. So if you calculate it and you see the minimum is via y, so now x has to change its information over here, and it's 3 now via y. Earlier it was directly x from x to z, which was 7, but now if x is going to z via y, it's around 3. So this is the minimum one and it is finalized. Now you will find that x is got some changes in its personal information. So until uh, there are changes in the personal information of a node, it will keep on sharing its personal information with the other neighbors present in the autonomous system, or its neighbors present in the autonomous system. So there are changes in x personal information. You can see this x to z, earlier it was 7, now it is 3, so there are changes. So in the next step, x has to share its information with the other two neighbors in the autonomous system. Now in the same way we will calculate uh, y's we will recompute y's personal information after sharing x content this one and z's content this one. So you can see over here that what all you need to do is you need to apply the same funda which we have used for recomputing the personal information of x in this y as well. So here after sharing x and z's personal information, this table becomes this. So 0 2 7 and 710 after sharing these two information, when y calculates its I should say recomputes its distance, or recomputes its table and distances to x, y and z, it doesn't find any shortest distance. So that is why it remains same. You can calculate it by your own, that 201 are the minimum cost to x, y and z respectively. In the same way, if now we are z is going to recompute its personal information after Z and Y shares their personal information with Z. So initially it's 027 and 201 by X and Z respectively, and you can see Z over here. The initial information was 710. Now after recomputing its personal information, you can see the change over here, that from Z to X with the cost 3 now. Earlier it was 7. It is all because of the node Y. So after getting the information from node Y, Z recomputes cost to all its destinations present in the node, and finds that there are some improvement, and then Z updates its routing table. So in this distance vector routing algorithm, the first step is this: when all the nodes prepare their personal information table uh, for sharing with the other sorry with their neighbors, not with the other nodes, because in distance vector routing algorithm, a node shares its personal information with its neighbors only. So first step is to prepare the personal information table. The second step is sharing the information with their neighbors and updating its own information using Bellman-Ford equation by using the other cost from the neighbors tables. And in the second step, if any node finds any update in its personal information, as you can see, X found the update over here, and Z found the update over here. So in the second step, X and Z both have found uh, some updates in their personal information in their table. So after having that change in their personal information, these two nodes in this autonomous system has to share their personal information with their neighbors again. So you can see in the third step that only these two nodes X and Z are sharing their personal information. Y is not sharing its personal information because Y is got no change in its personal information, which is 201 at the initial phase, and in the second step it remains 201. But you can see over here with the X, it was earlier in the first step 027 for X, in the second step it's 023, and for Z you can see earlier it was 710 in the first step, and in the second step it is 310. So these two nodes has to share the information with their neighbors again. So X will share its information with Y and Z, and Z will share its information with Y and X. Now again in the third step, all the nodes will recompute their information, and if they find any changes in their personal information, then they will again share the changed information or updated information with their neighbors, and if they do not find, then they will remain silent. So in the third step, you can see that after getting the information from their neighbors, none of them has any changes. You can see over here that X personal information in the second step is 023, and in this step it remains 023. Y's personal information is 201, it remains same 201 in the third step, and Z's information is 310, you can see 310. So what you can see over here is node Y updated its routing table, but its personal information remains same. It was earlier 027, because now X and Z recently shared their personal information with Y, and Y has updated its table, but there is no change in its personal information, but table is updated now because the information X personal information earlier was 027, and now it is 023. So it is 023 now, 23 here. And Z's personal information earlier was 710, and now it is 310. But after having these two changes in its table and recomputing the cost to the other destinations, those costs are remain same. So that's why there's no change in Y's personal information. So your routing algorithm ends over here, and these are the final cost. This will keep on going until you find any changes in any node's personal information. It will keep on sharing their personal information if there are some changes in their personal information. If there are no changes in the personal information, then it remains silent. So all the three nodes are settled down now, and these are the final cost to their destinations. So that is how distance vector algorithm works. See you in the next lecture.